Hello everyone, my name is Anvita Bansal and we are back with another lecture based on SDE Sheet. So the problem we are going to discuss today is based on matrix problem. So the question is median in a row-wise sorted matrix. So what you need to do in this problem is that you are given a matrix in which each row is individually sorted. If you check each row, they are sorted on their own, right? And what you need to find is find the median of the matrix. So how do you find it? Before that, let me quickly check if you guys are able to see me. Fine, cool. Okay, so let's understand the problem statement first. First of all, what do you understand by median? What is a median? So there is one important thing that is given in this question, that the matrix that you are given, let's say it contains R rows and C columns, right? So the total number of elements in the matrix will be something R into C, right? And this is always going to be odd. So you will be given such a matrix in which total number of elements, the count of total number of elements in the row are going to be odd numbers. Okay, so the matrix that you're given here is, let's see, 1 3 5. Let me take this. It's 1 6 5 2 3 9 and I guess 1 3 9 1 3 5. Okay, one 3 5 2 6 9 and 3 6 9. Okay, so this is the matrix that you are given. Now how many elements are there in this matrix? You can see 3 into 3, 9 elements. So in the sorted order, if I take all the elements in the sorted order, it would look something like this: 1 2 3 3 5, right? 6 6 9 9. That's how it is going to look like in the sorted order. Now what is important to understand, what is the median here? So count the number of elements, you already know that is 9. So what is the mid of 9? So mid of 9 is going to be 4, right? So what is the element at 4th index? 0 1 2 3 4 5 6 7 8. So this element should be returned as the median of your matrix, right? But you figured this median when you converted all the elements of this matrix into a linear array containing the elements in the sorted order, and then you checked out what is the mid element of this sorted array. That you can easily find out. You first convert this array into a linear array of all the elements, right? How can you do that? You can take an external array of length n into m, where n is number of rows and m is number of columns, right? So that will be the length of your matrix. Then you iterate over each element in each row and column, and you fill up this single 1D array that you have created. After that, you can use arrays.sort to sort the elements in that array, and then finally you can return what? You can return the n by 2th element from this array. This is one way in which you can easily do this problem. You can easily solve this problem. But the question here is, can you optimize this approach? Why? Okay, you are using some space here. You are using some space, and then you are using arrays.sort, which is n log n of time complexity, right? And some extra space. Can you do it without using any extra space here in this problem? So let's try to understand this thing. The key observation in this question is that if an element is the median, right? If an element is the median, you know one thing for sure, that it is the middle of all the elements in the array. So if this is the array of all the elements and this element is the median, which clearly means it is the middle of all the elements, means middle of the length of this array. So the number of elements before it are going to be equal to the number of elements after it, and that is equal to how much? What is the length of your array? That is 9. 9 by 2 is 4. So basically your median should have 4 elements before it that are smaller than it. You getting this point? So 4 elements should be smaller than your median if length of your array is 9. Right? So the observation here is, if I generalize it, the if let's say x is median, if I assume x as median of your array, and the length of array where n is length of your array, length, so there should be exactly n by 2 elements that are smaller than x. That is what, this is the point that I'm going to make use of while solving the question with an optimized approach, right? Okay. So the question here is, how can we do it without using any extra space? Let's take one example. I want to show you one example. In this problem, let me assume that 15 is your median. 15 is my median. Okay, just assume it. I randomly picked, and why I picked it I will tell you. Let's assume 15 is your median. So your question comes down to check how many elements are smaller than 15, are less than or equal to 15 in your matrix. When you calculate these number of elements, and ideally for this array, I'm talking right now about this array only. So the total length of array or total number of elements is 9. If I am assuming 15 as median, I have to ensure that I have how many elements less than or equal to 15? Total 4 elements. Why? Because length is 9. So 9 by 2 is 4. So if I am assuming 15 is your median, so somehow calculate how many elements are less than or equal to 15 in this matrix. If let's say you get some x number of elements that are less than or equal to 15, you will check, is x less than or equal to the actual number of elements that should be smaller than 15? If it is less than or equal to 4, we are going to do something, or if it is greater than 4, then also we are going to do something. Now what we are going to do, let's have a look at this in this example. Let me copy this. Wait a minute. I think let me write it 135,269. Okay, let's do it. You have this 135. I'm writing this again, and we are doing the dry run. 135,269, and what was it? 369. 369. Okay, so this was your matrix. Assumed median. I am taking an assumed median to be what? 15. Now I am checking how many elements are less than or equal to 15 in this matrix. So how to calculate it? you know, if you check that you are present here, you are present at this index, this is the largest of all the elements in this row. If I found out that yeah, this element is greater than this element, that means if it is smaller than this, that means all the elements are going to be smaller, right? Then I can make another check for as many number of rows I have. I check the last element itself. If it comes out to be less than 15, then I can definitely make sure that all the elements before it in that row are going to be less than. I can make the total sum of such elements, and for this case I will get how many? 3 into 3, 9 elements that are smaller than 15. And how many do we want? Actual needed, basically actual smaller elements that we need should be equal to 4 here, because that is 9 divided by 2. I'll not repeat why it's 9 divided by 2, because 9 is the total number of elements. I'm just taking this case. So this is what we want. Just keep the track yourself. But this is not very ideal way to check for each row linearly and then see what is the last element and then make your calculations. Rather, we know each array is sorted, right? Each row is sorted in this array, sorted rows. So I can apply binary search on each row. Binary search will do what? Binary search will reduce the time complexity of searching the smaller elements from, actually I was making comparison for each element. So for each element I am going and checking, and then that will be linearly for each row, and comparisons will be n minus 1. So from n square of time complexity, can I reduce it to n log n? Yes, I can. So let me use binary search on each row. When I do that, what can I do? So first I check that 15 is the assumed median. I want to ensure how many elements are smaller than 15 in this array. So I go in the first row, use binary search here. I find mid value as 3 is less than 15. Then I take my smaller element. For that, the prerequisite is that you should know binary search already, which I am not going to repeat here. I am directly going to use the concept of binary search. So 3 is the smaller element. Now this was the mid, so I increment the count of start to mid plus 1, which eventually comes down to this end index of this row. So end and mid are both pointing to 5, which is also less than 15. And now your start again goes to mid plus 1. So mid in this case was this element, the index of this element. Now when you do start plus 1, 0, 1, 2, 3, start will come to third index, that means the third column. So this element, this index tells you that these are the number of elements that are less than 15. So you get 3 from here. So basically you are doing an iteration that is like this. You are doing an iteration. Let me write it here. See, this problem needs you to understand very keenly the steps that we are discussing here. It's more about that. Writing code will be the last part as usual, but very importantly you need to understand. So basically for int, I starting from 0, I is less than rows, I plus plus. Okay, for each row I have some start index. Start is 0, end is last column minus 1. Let's say C was the number of columns. So while this is the typical binary search, start is less than or equal to end, I calculate mid, which is start plus end minus start divided by 2. If your ARR of mid, or I'll tell you in matrix how you'll write, you can do that. I'm just simply writing ARR of mid here, whatever that is. If ARR of mid is less than or equal to your assumed median, then what you are going to do? If it is less than or equal to assumed median, that means you can go ahead, right? So you can easily do start as start plus 1, mid plus 1, right? In else case, what you're going to do, your end is going to be mid minus 1. Let's say for example this value was 20, so obviously your end would come at this position. Okay, so that's not the case here. Anyways, why we have done so, I'll tell you. Okay, so when I checked for this mid value, which was 3, I came at this position, I came at this line of code. Error of mid is less than my assumed median. That is true. So start becomes mid plus 1. Start points to at this index, which is 5, and end index was already here. Now what is my mid? I again come back to this loop. Mid is start plus n minus, which comes down to 5 only. I check for this condition. Mid is again less than, what is my assumed median in this case? It is less than 15. So again start becomes mid plus 1, but here it goes out of bounds. So out of bounds means start is greater than end here. That means this condition will fail. When this condition fails, you know one thing, that from one row, that was the row for which we were iterating currently, you have found number of elements that are smaller than number of smaller elements. You can write smaller elements that are basically, these are the number of elements that are less than your assumed median. So that will be equal to, actually they start will be added to the number of smaller elements plus equal to start. Now why start? Why I am adding the start index? See, you only came out of, now this is after this while loop ends. This value you are updating after your while loop ends, and this is within your for loop. You need to understand this part very importantly. When I have already come at this position where my start has exceeded the index of your end index, right? End index has been already exceeded, which means that all the elements in this row must be less than your assumed median. Only then this condition has come. So ideally 0, 1, 2, 3, start is pointing at 3 index right now. And how many elements are less than my assumed median? Less than or equal to 3 only. So you can add at least 3 for this particular row to get how many elements are smaller than 15. So you can assume that actual smaller element, you know that actual smaller elements was 4, and you are also simultaneously keeping a track of number of smaller elements which you have defined as a variable above this for loop, small elements, and you initialized it to 0. Okay, and then within this for loop you are calculating and incrementing the count of smaller elements as and when you are getting. Okay, so this part is done. Now you come to the next row. You check how many elements are smaller. Again apply binary search and you will find out all 3 elements are less than 15. So this 3 will also be added. Earlier it was 3, now it becomes 3 plus 3, 6. Okay, then you come to this row using this for loop. You are at the last row for this iteration. Now how many elements are less than 15? Again 3. So 3 will be added, so you get 9 elements. Now wait, you have got number of elements which are smaller than 15 as 9. And how many elements should have been actually smaller than 15 for it to be, for our assumed median to be actual median? 4, which means that number of smaller elements that I am getting, that is equal to 9, and actual smaller elements should have been 4. If smaller elements is greater than my actual elements, what does this mean? That I am getting, my actual small should be 4, but I am getting way more than that. So my assumed median should be less than 15, so that maybe I get number of elements which are less than 9 and somewhere close to 4, correct? So this is what we want. So do you think of again something, that whatever median we are assuming, we can apply a binary search on that range also. Here let's assume I started with the range of 1 to 15. And why this 15? I will tell you, don't worry about it. Just try to understand that, okay, I have assumed one random value, and let's take this range to be from 1 to 15. Let's say I am taking this range of median from 1 to 15, and initially I took some median which was 15. Okay, let it be like this. Now I got to know that number of elements less than or equal to 15 elements, those should be actually 4, but I am getting them to be 9, which is way more than the required elements for 15 to be median. So definitely this cannot be the median, and let's take a value less than 15, so that maybe I can get elements closer to 4 which are less than that element for it to be median. So apply binary search on this as well. So now my range becomes 1 to what? 1 plus 15 minus 1 divided by 2, that is basically the mid of these two elements, that will be 8. So let's assume my assumed median will be 8 now. So now you need to find number of elements less than 8, less than or equal to 8. If they are equal to 4 or greater than 4, less than or equal to 4 or greater than 4. Okay, now our assumed median becomes 4. Let's check for 4 now. Okay, let's check for 4 in this case. So our assumed median is 4 or 8, sorry, 8. Fine. Now again do the same iteration for all the rows. How many elements are less than 8 in this row? 3 elements. In this we get, I will keep writing it here also. So let's keep updating number of smaller elements and actual elements. Actual elements you know is 4. I am just updating number of smaller elements. So number of smaller elements. So that is coming out to be how many? 1, 2, 3, 4 smaller elements, and our assumed median is already, assumed median is what? Already we know that is 8 right now. So number of smaller elements than 8 in this entire matrix will be 1, 2, 3, 4, 5, 6, 7. So there are total 7 such elements which are less than or equal to 8. Okay, so 7 is 7 equal to 4, less than or equal to 4? No, it is greater than 4. So definitely you should reduce the size of your assumed median again. Now your assumed median should be what? Actually we did something, it should have been earlier, I took 15, right? So when we are applying binary search on this range, so end should be this value minus 1. So 14 plus 1 by 2, so that should have been ideally 7, but okay, let it be 8 as of now. Fine. So you were checking for something like this. Now 8 is also discarded. Why? Because number of elements are greater than 4 if we are assuming 8 as our median. So let's reduce what? Our mid in this case would have been 4. So 4 minus 1, 3. Okay, let's assume that mid minus 1, our actual value we were finding out was 8. What is the middle of 1 to 8? If this is the range, what will be the middle value? 4. If I take 7 as the end index now, that is what I am trying to do. Okay, so 1 plus 7, that will become 3. So I am now making this assumed median as 3. Fine, make it 3. See, for this step to understand, if you are facing any issue, you should understand binary search properly. So I will really recommend you that in order to understand this question, you should have a good grasp over binary search, which is not very difficult, it's very easy. Okay, now my assumed median is 3. Fine, what I am going to do, check for elements less than, assumed median becomes 3 now, and number of smaller elements, let's check how many are less than or equal to 3. 1, 2, 3, 4. So there are total 4 elements. So 4 is equal to 4. So whenever I get number of elements less than or equal to the actual number of elements, then I am doing what? I am doing my start as mid plus 1. Okay, I am doing it mid plus 1. So now in this case my mid was 3. Now I will make my assumed median as 4. Okay, so my assumed median will become 4 now. Okay, did we already check for 4? Let's check for 4. Now elements that are less than or equal to 4. How many are those? 1, 2, 3, 4. 4 only. So again in this case we will increment the count by 1 of this assumed median and we will make it to 5. Now let's check for if our assumed median is 5. Okay, how many elements are less than or equal to 5? So 1, 2, 3, 4, 5. So there are total 5 elements which are less than or equal to 5. Now what? Your number of smaller elements is greater than 4. It is greater than 4. So this means if it is greater than the elements that you required, what I can do is I should, one second, number of elements, just a second, it came out to be 5. This should ideally be less than or equal to 4. So when it came out to be greater than actual requirement, what you can do, you can again reduce the size of it by 1. But wait, what happens is when you also have to simultaneously keep the check of your end index. And while we were making changes into the range, we started from 1 to, I randomly chose 15, then we chose the mid value, that was 8, and then I chose mid value of these two, 9, that is 8, 9 by 2, that will become 4. Okay, I checked over 4. Now your range will be what, 4 to 8 something. When we were doing it was 4 to 8. Then I checked for mid of these two, that will become 6. I did not check that. So simultaneously I have to keep a track that your start should be less than or equal to end, right? And in this case, in the case when your start will exceed the value of end, that means the assumed median is correct that you assumed. Okay, your assumed median was correct and you should return start in that case. So what we are doing actually is that we are applying 2 binary searches. One binary search on our range. Now coming on to the point why I chose 15. I just randomly chose 15 just for the sake of explaining this question. What we are actually going to use here is that, see, your question says that total maximum value of your matrix can go up till 2000 and it starts from 1, means any value in this matrix can be maximum 2000. So I can take the range of 1 to 2000, 1 to 2000 as my range, in which I will assume median initially to be middle of this 1 to 2000, that will be 1 plus 2000 minus 1 divided by 2. That's how you calculate median value. And then I will apply binary search on this range each time and then calculate the number of elements smaller than or equal to that median that I have chosen, and on that basis I will apply binary search on each row and take my decision. Okay, so that is about this problem for you to understand. Now we will once code, and after coding I'll come back again and explain to you once again using this 2000 as my range. Okay, so let's see how we can solve this problem. Meanwhile, let me check if you guys have any doubts. Okay, one second, give me a moment, let me just, I'll come back to your doubts, guys. Hi everyone. See, so the best part about this SD sheet is that the questions that we are already taking in this SD sheet are very good for you if you want to be, literally you are starting either from scratch or you want to be interview ready. This sheet is extremely good. It has been designed very well. I'll suggest you keep practicing every day. Try to learn as much as you can, code on your own, and we already, each question that I take in Java only. So if you want to come back and see how can we code that particular problem, you can always come back to the video. And there are always more than one approaches possible, not always. Okay, many questions might not have, but yeah, we try to solve the question using the most efficient one, although I start from the brute force approach. And like in this problem also, you can use priority queues to solve this problem, which I tried also, but that will not lie under the expected time complexity, and it will fail for around, I guess, 20 test cases, somewhere around 20 test cases will fail. So I always suggest you to do some brainstorming on your own and then come up with any approach, code it. You'll fail. If it fails, the submission fails, no worries, at least you will understand why it failed, and then you come to the optimized approach, be it by your own thinking or even if you try to understand it from some video, that's completely okay. So now let's move to code so that you can understand it. And let me see if you guys still have any more doubts. Okay, fine, then let's move to the code now. Cool. Starting off, let's take my int start as 1. This is the median value that I'm going to choose, the range of my median value, and int end as 2000. Fine. Then int median, I'll take it later on. Now you want to keep modifying the value of median because you are assuming some median, right? You have to modify it till start is less than or equal to end. Let's say int assumed median is equal to start plus end minus start divided by 2, right? That's your assumed median. Now what you want to find is that whatever is the assumed median, you need to check how many elements are less than that. So let's take, for example, int number of elements count. This is the count of smaller elements. Let's say you are getting this count from some function which I will be writing in a helper function. I'll tell you what arguments I will pass in it. Let's forget about it. Just assume that this is your assumed median, which lies between the range of this and this, right? And then you are checking in this matrix, this helper function, let's say, is trying to get us how many elements are less than or equal to my assumed median. Then you will check if the smaller elements count, if this count is less than or equal to the actual count that we need. And what is the actual count? If this is less than or equal to actual count, right? Let's also define an actual count. So first tell me what is the total number of elements. So int n, let's say, is r into c, right? So actual count represents actual number of elements that should be less than or equal to this assumed median, right? So in this case, if the total length is 9, you should have 4 elements less than or equal to it. So actual count represents that. So actual count should be r into c divided by 2. That should be your actual count. Okay, then you will compare the count that you get from by applying binary search on each row. If that count is less than or equal to your actual count, then what do? You do what? If it is less than or equal to your actual count, that means your start index should be equal to your median should be your assumed median. Where is your assumed median? Plus 1. In else case what? In else case, if it is greater, that means shrink that window. Your median should be reduced. The size of your median, not size, the amount of your median should be reduced. So your end index will come at assume. Let me copy this one. Command V, and it should be less than by 1. Okay, so finally I explained you. I'll tell you again because this part is a bit tricky to understand. Not tricky also. If you just do one dry run, you will understand. Then you return start index. This is what you are doing. Now let's do one thing. Let's write this helper function. So this is one binary search that you are applying on the assumed median values, for which you chose this as the range as it was given in your question, and we made use of that rather than picking any element randomly from your matrix, right? So public static int helper function is giving you how many elements are smaller than that assumed median. So int matrix you are passing, I am passing it as ARR, and int assumed median is what you are passing. Fine. So I am passing these two values. Now you again apply binary search. For that, what you do, let's take your int start for int, for each row, for int, I equals to 0, I is less than arr dot length, right? I plus plus. Then you choose your start value. Int start equals to what? 0th index. For every row your start should be 0, and for every row your end index should be equal to this last column index. So that should be arr 0 dot length minus 1, correct? Now you want to find out how many elements are less than the assumed median. So while your start index is less than or equal to end index, you are calculating some mid, which is start plus end minus start divided by 2, right? Cool. Then you check if that value, if your mid, this is index, this is the index of the column for that particular row. So that element would be matrix of I, that represents row, and mid, which represents column. So if matrix of I, matrix not arr we are passing, arr of I mid is less than or equal to assumed mid, then what? If it is less than or equal to assumed mid, that means you can shrink the window size and you can make the end as mid minus 1. In else case, what you do, you make your start as mid plus 1, the whatever mid you chose, and that should go till start is less than or equal to end, right? This is something that I am doing in order to calculate how many elements are smaller than or equal to the assumed mid. Now wait, you have not yet calculated how many elements are less than or equal to assumed mid. So for that I am doing, for each row, int, let's say answer will tell me how many elements are less than or equal to that assumed mid. When I come out of this while loop, okay, and staying within that particular row, wherever my start index is pointing, I explained you that will give me the number of elements that are less than or equal to assumed mid. And after each iteration on the row, after iteration on every row, I will get my start index, which will be exceeding either the end index or the exceeding your start index. So that will basically give me what is the number of elements that are less than or equal to the assumed mid, correct? So then I finally what I would want to return, answer, and this is what I'm passing to my median. So let me also give the arguments for this helper function, which is matrix and assumed median. Okay, is that what I wrote? It's median, capital MED IAN, and smaller element count is getting copied to this, and actual count is this is small a, actual count, start assume median, start end. Okay, start end, let's check and we will see if we have any issue here. 47, this C is also small. Assumed mid 62, assumed med, okay, that is MED, median MED. Anything else? Let's check. Okay, we are getting some error here, let's check it. So why is it 2000 plus 1? Actual count R into C divided by 2, while start is less than or equal to end, you are calculating your assumed median every time, which is start plus end minus start divided by 2, fine. Then you are calculating how many elements are smaller than using this helper function. If the count is less than or equal to the actual count, which is this, then your start is, then you are incrementing the count of your median, which will be assumed median plus 1. Okay, fine. Assumed median otherwise it's assumed median. End is assumed median minus 1. What else? Let's check it. Is less than or equal to actual count. Okay. Answer is 0. I don't think I have made any mistake here. If you guys find any issue, you can tell me. Okay, let's check it one by one. We start from 1 and our end is 2000. Cool. Then your actual count is R into C divided by 2. Now while your start is less than or equal to end, okay, this is fine. You start from this value, your end is this. You are taking some assumed median, which is start plus end minus start divided by 2. So you are taking some smaller element count, which is your this. If smaller element count is less than or equal to, then you are making your start as median. Otherwise this is fine, I think. Then you checking for helper function. If it is less than, fine. If end is error of 0 dot length minus 1, that is also fine. Start is less than or equal to end. Mid is start plus, fine. Error of I mid is less than or equal to assumed median, fine. Less than or equal to okay. Mid minus 1. Let's check now. So this is all about this problem for today, and I hope you have understood this problem. So basically we have used binary search 2 times here, okay, and we have not used any extra space, fine. This is what we have done for today. If you have any doubts, you can ask me. Let me just check if you guys have any doubts. Wait, let me open the video section. Sorry. It's not ended. I'm just opening up the screen so that you guys can see. Okay, I think you guys are able to see my screen. Fine, so that is about today's problem. If you have any doubt, you can write in the chat. Otherwise we can end this session for today. So this is, I'll tell you that this is a very good problem. This is a very nice problem. It will make your concept of binary search very clear. So first important thing to note for this problem is, if you do not know binary search, do not attempt the question. First go and see the video on binary search that we have taken up in searching and sorting. Then come back to this problem and solve it. Second important thing is, you can solve this problem using, you can try it using priority queues also if you know, but it does not take time, expected time complexity. It exceeds the time complexity in some of the test cases, not all. I've already discussed that thing, so you can try using that also. I think I might have, no, this is not that. So yeah, this is the one I think that I did. using priority queue. So this is the priority queue solution, which you can try. Obviously it will fail for how many test cases you can see here. So 11 many test cases, not 11, I think 111. So this is the code that I wrote. That is all about today's lecture then. Thank you everyone. Bye bye, and I'll just show you the actual code again. Fine. Okay then. Let's end this and see you all in the next lecture tomorrow. By day after tomorrow. Tomorrow I'm not taking any class. I'll take it on day after tomorrow. Bye everyone.